Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Almost every calculus and algebra student knows how to use the arithmetic series formula. You write down the formula, you substitute in your values, and out pops the answer. But if you're aiming for a top score in AP Calculus or IB Math, simply memorizing formulas isn't enough. The exam boards want to see if you understand the structural fabric of why the math works. Today, we aren't just practicing questions. We're going to formally prove the arithmetic series summation formula from scratch without using induction. Then we're going to tackle two advanced elite level exam problems that blend arithmetic series with logarithms and systems of nonlinear equations. Now, before we jump in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. So here we have the arithmetic series formula. Now we know that S sub n is equal to the sum of all the terms in the arithmetic sequence. So that means it's going to be u sub 1 plus the second term, which is going to be u sub 1 plus the common difference d, plus the third term, which is u sub 1 plus 2 times the common difference d, plus dot dot dot. And this is going to go all the way to the second last term, which is u sub 1 plus n minus 2 times d. And then the last term is going to be u sub 1 plus n minus 1 times the common difference d. And now we're going to write this sum again, but this time we're going to do it backwards. So we're going to start with the last term, which is u sub 1 plus n minus 1 times d, plus the second last term, which is u sub 1 plus n minus 2 times d, plus all the way until we have u sub 1 plus d and u sub 1. Now let's take a look at what happens when we add these two equations together, term by term, vertically. So we would have s sub n plus s sub n. We would have our u sub 1 plus the last term. And then we have our second term plus the second last term, all the way to this one plus this one, and then again the last term plus the first term. So we're just adding them together vertically. Now the left-hand side, that is going to be 2 times s sub n. And then the first one, that's going to be 2 times u sub 1 plus n minus 1 times d. And then the second term is going to be 2 times u sub 1. And then here we have n minus 2 times d plus a d, which means we have n minus 1 times d. And then we're going to keep adding. And then the second last one, again, that's 2 times u sub 1. And this is just the same as the second term. So this would be plus n minus 1 times d. And then the last term is just the same as the first term. So that's 2 times u sub 1 plus n minus 1 times d. So now if you look at this, all of them are identical. They are all 2 times u sub 1 plus n minus 1 times d. And we know that there are exactly n terms in each series. So which means there's going to be n terms of these. So this means we can rewrite this as n times 2 times u sub 1 plus n minus 1 times d. And this is equal to 2 times s sub n. So now all we need to do is divide both sides by 2 and we can solve for s sub n, which is how we arrive at the formula s sub n is equal to n divided by 2 times 2 times u sub 1 plus n minus 1 times d. Now that we have proved the formula, let's take a look at our first example. Here, the sum of the first 3 terms of an arithmetic series is 24, and the sum of the squares of those same first 3 terms is 242. So this means we have u sub 1 plus u sub 2 plus u sub 3 is equal to 24, and then we have u sub 1 squared plus u sub 2 squared plus u sub 3 squared is equal to 242. And we're asked to find the two possible values for the common difference d. Now we know that we can express u2 and u3 as an expression in terms of u1 and d. But we're going to be a little bit smarter here, because we're going to be squaring those terms later, and if we expressed everything in terms of u1 and d, there's not going to be any symmetry. So the trick here is to express everything in terms of u sub 2 and d. Since u sub 2 is equal to u sub 1 plus d, that means u sub 1 here is equal to u sub 2 minus d. And u sub 3 here is going to be u sub 2 plus d. So now from the first equation, we can see that there is very nice symmetry. We have a plus d and we have a minus d. So when we add them all together, they're going to cancel out, which means we get u sub 2 minus d plus u sub 2 plus u sub 2 plus d is equal to 24. With the d's canceling out, we end up with 3 times u sub 2 is equal to 24, which means u sub 2 is equal to 8. Now we're going to take this and substitute it into the second equation. But again, we're going to express u sub 1 and u sub 3 in terms of the second term and the common difference d. So we end up with 8 minus d squared plus 8 squared plus 8 plus d squared is equal to 242. Expanding out the squares will give us 64 minus 16d plus d squared. This is the first one, plus 64 plus 64 plus 16d plus d squared is equal to 242. Now the minus 16d and plus 16d will cancel, so we end up with 192 plus 2d squared is equal to 242. Moving the 192 over gives us 2d squared is equal to 50, which means d squared is equal to 25. So therefore, square rooting both sides and taking the positive and negative solution, we end up with d is equal to positive or negative 5. So these are your two possible values for the common difference d. So just a quick note here, we expressed everything in terms of our second term and the common difference d. But if you had actually went and expressed everything in terms of the first term and the common difference d, you'll still end up with the same answer. The only thing is that you won't get this nice cancellation here in the middle, so you're just going to have to work with a quadratic equation that's a little bit more difficult to solve. Now moving on to our second example. Here we have an arithmetic progression where the first term is ln of x, and we know that the common difference is ln of 2. And we're asked to show that the sum of the first n terms can be expressed in this form here. So we're going to start with the formula for s sub n, and that is equal to n over 2 times 2 times u sub 1 plus n minus 1 times d. Now substitute in the values that we have. This is n over 2 times 2 times ln of x plus n minus 1 times ln of 2. If we distribute the n over 2 into the bracket, we end up with n times ln of x plus n times n minus 1 over 2 times ln of 2. Next, we're going to apply the logarithm power law, which says that if we have k times ln of a, this is the same as ln of a to the power of k. So that means we get this is equal to ln of x to the power of n plus ln of 2 to the power of n times n minus 1 over 2. Next, we're just going to distribute this power here. So we get this is equal to ln of x to the power of n plus ln of 2 to the power of n squared minus n over 2. And finally, now we're going to apply the logarithm power law, which says that ln of A plus ln of B is equal to ln of A times B. So therefore, this is equal to ln of x to the power of n times 2 to the power of n squared minus n over 2. And that is exactly what we're trying to show. And now let's do a quick recap of what we covered in this video. We went over the proof for the arithmetic series formula, and it works by taking advantage of vertical symmetry. When we add the series to its reversed reflection, it creates n identical pairs. We saw an example of how logs work with arithmetic series. When the series parameter contains logs, you can apply the power rule to the coefficient and the product rule to the separate terms so that you can condense it into one expression. And lastly, we learned a trick to use symmetry to our advantage. While we can express every term as an expression of the first term in the common difference d, sometimes it's easier to express it as another term in the common difference d, so that the symmetry can help us eliminate some terms and make the algebra much easier. And lastly, these types of questions can always use math that you might have learned in previous chapters. So when you see that, don't panic, just slow down and deconstruct the problem to see how the relevant pieces you've learned fit into this larger puzzle. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other sequences and series topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.